very exhausting, and so I have to try to keep these very hard trips and very from the time size, but also I find this very exhausting. So that's why I have to be economic.
Recording in progress.
Yeah. So it seems like we have 10. We have 8 o'clock. So let's see. Maybe I'll wait 1 minute to have a few more people coming in, because we not even have the second speaker here yet. So that's hope that's nice that Alexander is here. Then we have Prokopis here. It's also very good. And Jan Fei and Yu, that's great. And also Suji Bu is here. That's good. He's also, I think, a speaker later. So let's wait till 1 minute after. We have a tight. It is 1 minute after already. We have a tight schedule today. So let me just start. So today we have, I think, 14 distinguished speakers today. So I'm very much looking forward to the day. We have 3 sessions. 2 sessions in the morning for us, right? For you, it's I guess evening, and there's another one which is very late, which I guess it's too late. Also, Matteo is here. It's very good. Yeah. So it's always good to see. He wanted to make sure he makes your talk also. So we have these 3 sessions, and it is a bit tight schedule, so we should try to be on time, right? I mean, that we leave a bit of time, and at least 1-2 minutes at the end for 1-2 questions is, I guess, the minimum. And that we have also a break till the next session. So the first talk, it's all morning. In fact, I have all friends here, so that's for me is a big pleasure, and I really wanted to share this one. And I usually don't do that, but I said, if you have 4 friends, that's it's great. And so the first one is someone who I've been working for a long time. And I don't know how many papers we have, but I can say many. And you've been 6-7 years with us, and now a big professor in China. And so the first 2 talks will be on vortex beams. I think the first one on gamma vortex beams. So please, the stage is yours, Zhangqing.
Thanks a lot. Okay, I now start to share my screen. Okay, can you see my slide? Yes, so it's fine.
Sorry, very, very nice. My tone was gone, so I see everything very nicely. Yes.
Okay, very good. Okay, so let me start. So first, I appreciate. This conference invite me to share to give me the chance, and I very like to share our very recent work with all you. Today the talk is about use a strong laser to generate the vortex gamma photon beam. Here we consider the single gamma photon is vortex. And also I will also mention a little bit use the vortex gamma photon to interact with nuclei. And finally, I will introduce how to generate the dense polarized positrons directly by laser plasma interaction. Not by previous work, laser electron interacting, blah, blah. We directly use a laser shooting on plasma to generate very dense and polarized positrons. Okay, let me first start with what is the gamma photon stuff. So as we know, here we think about the single photon. The self is vortex, means, the wavefront is a vortex. So normally we can see from those figures, that means, so they have a vortex wave. And we also can see from the wave function, we can see their phase is vortex, okay? So if we have those vortex gamma photon, we can do like the nuclear physics or particle physics, because there are many interactions rely on not only the spin angular momentum, also the orbital angular momentum. That's why we want to know, because previously we have many papers how to generate like polarized gamma photon, or even the spin polarized electrons or positrons, blah, blah. And now we are focusing on further to see how to generate the gamma photon itself have orbital angular momentum. Okay. So typically we know for the low energy photon, we can generate by many methods, either by some like a phase plate, we can, or for the, for the high energy, the X-ray, you normally use like the undulator, or we can consider some regime like is a free electron laser. It's like that. If the undulator have rotate, finally, we can get some like X-ray, also have the orbital angular momentum. But unfortunately, so far, for the gamma photon, use a free electron laser method, or use some other the very traditional method, we can generate the vortex photons, but either the photon energy is lower, or normally it's EV level, or if we have like the X-ray photon, photon, that means normally the orbital angular momentum is for low order, some like the topological number is 1 or 2, and not very high. Okay. So, but recently we also have many methods to how to generate the vortex gamma photon use strong laser. We normally use like strong laser. Use a vortex strong laser interacting with the electron or plasma. Then we think about, okay, it will generate the vortex gamma ray or gamma ray beam. Yeah, but we know that for typically if we can use a strong laser directly interact with the electron or plasma, the electron will radiate the gamma photon via the nonlinear quantum scattering. But for here, during the nonlinear quantum scattering source, the gamma photon is not coherent, and also we do not know exactly what's the single photon orbital angular momentum. We typically think, okay, if we look at the angular distribution of the gamma photon, it has some rotate or rotating signature, but we do not know the single gamma photon itself. The orbital angular momentum. That's why now there are also many works focusing on how to generate the vortex gamma photon. Consider the orbital angular momentum, or consider the angular momentum conservation. Normally we know we can use the electron interacting with the laser, and if the electron absorb many photons from lasers, then radiate one high energy gamma photon from the angular momentum conservation or angular momentum transfer, we can generate the vortex gamma photon from the spin angular momentum transfer. For example, in our recent work, we consider the electron beam interact with a circular polarized laser. Circular polarized laser, typically one single electron absorb many laser photon, but here the laser photon only is a circular polarized, not the laser is not a vortex. That means initially the angular momentum is electron spin angular momentum, and also the laser photon is a spin angular momentum. Finally will radiate one single gamma photon. Since the angular momentum conservation, we will know the final gamma photon will itself have the orbital angular momentum. And since here is the radiation is not coherent, and also the gamma photon itself is not like is a pure state, it's a mixed state. That means the gamma photon itself is a mixed by the mixed vortex states. That means the topological number can be a mixed. There are many states. Okay, and if you want to see the details, because we can here in this method we consider here in our here we consider nonlinear quantum scattering. We consider the I mean, the cross section and the probability, radiation probability, we fully consider the angular momentum conservation, and we developed those methods. And in our we already put in archive, so you can see many of the calculation details. And finally, we will give some pictures like this. Finally, the gamma photon have the many states, have many states. But here, unfortunately, we cannot, so far for in this work, we cannot control the gamma photon, the orbital angular momentum of the gamma photon. That means it's a mixed state. In this work, we do not know. We do not know how to control or how to generate a pure state of the vortex gamma photon. But recently, very recently, we already have some methods, how to generate the pure state gamma photon. Okay, but that work is under preparing. Okay, so and the next question is think about the gamma photon itself is a vortex, but how to measure the orbital angular momentum of gamma photon. Actually, in this work, we also use one method by the nonlinear Breit-Wheeler process. That means if the gamma photon is vortex or not. Finally, the pair. If we detect a pair angular distribution is totally different. From that, we can distinguish how large is the orbital angular momentum of the gamma photon. But to be honest, this method is not. Cannot use very well, because if we consider another case, if the laser. Because in this method we need another laser laser. This is very difficult in experiment, and also if we consider if the gamma photon is not as high, the energy not as high as the MeV. Normally, like the few hundreds the keV. How to measure or how to detect. Also, we also have a recent work. We also have a recent work to detect the orbital angular momentum of the gamma photon by the photonuclear reaction. We can detect that. Okay, we already put in archive. And except that, actually, we also have some other work. We are focusing on how to measure in experiment the vortex of the gamma photon. Okay. So if you can find more details in our recent work. And the next, I will mention a little bit how use a vortex gamma photon to do the nuclear reaction. Normally, if we gamma photon is the plane wave is the gamma photon, the wave front is the plane wave. That means if the gamma photon interacts with the nuclei will be excited to the different states. We can say E1, E2, E3, and the probability will goes down. But if we use a vortex gamma photon, we found here we first developed calculated the cross section use a vortex gamma photon interact with the nuclei, and we found some very interesting phenomenon. Is if you can see this picture, if we have the vortex gamma photon, and for some case we can, the E1 state or some states will be forbidden, and also we can excite some pure. We can excite the nuclei to some certain state. That means. Probably in the future, we can use this method to think about how to generate the gamma photon laser by this method. We can but that will work we are working on actually. Okay, and here I will show here, as I mentioned just previous, we can detect mixed. The orbital angular moment state of the vortex gamma photon by the nuclear reaction. If you see the signature is different. Okay, if you want to see more detail, you can see our in our recent work. Okay, so The last the topic is about how to generate dense polarized positrons. And okay, we know there are broad applications. If we use polarized positrons, they can to generate. The polarized positron can use to precisely measure the effect of the weak mixing angle, or there are many other applications. And recently, we have normally, in traditional method, we use like in the Sorry ring, use a so-called turnoff effect, or as our recent works, there are many works, we use a laser interacting with the electron, or laser interacting with the gamma photon to generate the positrons. And the idea is first use a nonlinear quantum scattering to create the gamma photons, and further have the nonlinear Brita-Wheeler process to generate positrons. And typically, if the laser field itself is not symmetric, and then finally the positron will be polarized. Okay, that's a very typical idea, and recently many works on that. But the question is, the question is, if we use the typical, use a laser interact with the gamma ray or electron method. The problem is, first we should consider the laser, interact with the electron or the gamma ray that generates the density or the emission angle, the emission angle of the positron is very large, and also the energy spreading of the positron is very large, and also the density is very low. That's very seriously limit the further applications. Here we give some numbers. Is use a typical method, like if you use this in the Sorry ring, the positron parameter. The polarization normally can be large. Can be large. It's can above 90%, but will take the time long, and also density is low, because typically in Sorry ring the density of the particle is low. And if we consider use the gamma photon to interact with the laser via the nonlinear Brita-Wheeler method, normally the average polarization of the positron only is 30% to 40%, and also the density is low. And okay. So if we consider some other methods quite similar, normally the average polarization is low, because if we want to use some specific experiment, we can require the positron polarization is above 60%, and also we normally need a very high density. So that's those are a great challenge. So in our recent work, we consider and directly use a laser shooting on a plasma. The main idea is, typically if we are laser shooting on a plasma, first the laser shooting on a target, the surface will be ionized. Then the electron will be X-rayed. Then emit gamma photon by the nonlinear quantum scattering. Okay, this is very well known. People know that. Okay, and also the gamma photon will further create the pair via the nonlinear Brita-Wheeler, but not here. The gamma photon generate the pairs in the mixed field is by the driven laser and the plasma field, because when the electron move on the target surface, will generate a very strong magnetic field. Okay, this setup we can understand easily, but here the crucial effect is we should control the solid target, the angle, because here we have an angle. If we directly shooting on, 90 degree shooting on, then for that method we typically need the laser should be very high density. Should there should be 10 to 24, 10 to 25 watt per square square centimeters, and because that cannot accelerate the electron to high energy. And and the next crucial effect is we should control the laser polarization angle, because if in our previous works, why we use the electron interact with the laser, why for that case the positron polarization cannot be very high? Because I mean the gamma photon polarization frame and also the pair creation frame, they are in the same laser field. That will limit the polarization degree. But here, if we switch the driven laser, can see switch the driven laser polarization with respect to the foil. That means the driven laser field will have an angle with respect to the magnetic field created by the electron. Then finally will create a very high polarization of positions. So in this method, finally we can get the average. Here, the average polarization degree of the positron is close to 70%. This is the average polarization, not is some like a partial. It's an average polarization. If you see the partial can be close to 90, even 100%. This is very high. And also because here with the laser shooting on the solid target, finally the position density also very high. This can be 10 to because it's you can say 10 to 18 centimeter cubic. This is very high. And if you see is near to the 0.2 peak. And the average energy of the positron is roughly 300 MeV. Okay, this also we already put in the archive, so you can see the details. Here is our 3-dimensional QUD-PIC simulation results. Okay. Let me go faster. Here we give some the parameters how to for the experimental feasibility. If we change, this angle is the solid target with respect to the ground. Here's the angle, and the second B is the laser polarization angle with respect to the foil. Okay, here is if we use the laser intensity, we can see if laser is 300, even lower, we still can generate a very high polarization and a very dense. Okay, so this is close to our current laser facility. Okay, here also we consider if the target, the target also have the pre-pulse, okay, or the target length, we consider that effection. If you see more details, you can find from our recent work, okay. And people will have another question. Okay, if we change the target, the structure. For example, we consider coin target. For coin target, this is also well known in the laser plasma interaction. For this case, we will have much higher laser intensity, but the polarization will be lower. Okay, we also explain more the reason in our work. Okay. And also in this work, we already to consider other probability, because there are many, if the laser shooting on the plasma, there are many other effects like the Betz-Hitler effects, also the coherent scattering. Also, we consider the other effects. For that we already take into account in our method and in our work. So all that we can say not important. Okay. Okay. Then another our recent work is we want to how to control the polarization of the in the quantum scattering, because we know if the laser intensity is higher, if the laser interacts with unpolarized electron, if the laser intensity is higher, laser intensity is higher, then the gamma photon polarization will goes down. But the brilliance of the gamma photon will be higher. But then if we want to simultaneously to have a high polarization and a high brilliance, then we should know how to control the polarization. Here we know if we found if we see a multi-photon absorption channel, the gamma photon polarization is controlled by the electron spin. Otherwise, for single photon absorption, that is controlled by the laser polarization. Okay, you will also can find some details in our work. Okay, so finally, I will introduce our another recent work. We already put our QUD particle, QUD-PIC code. we consider, we name it the spin resolved laser interacting with the plasmas. In our in this work, we introduce the details how to implement the spin effect in our code in the P code. Also, here we just we only introduce our the first version actually and now we are preparing the next versions. In our next version, we will consider the fusion and the gamma nuclear reaction, and also in our we also include our the machine learning methods, and this already close to done because and also this is our the data structure our code. And here, you can use it very easily. We already consider many methods. Okay, so finally, okay, due to time reason, I will thank my collaborators. Of course, I also thank Christoph and Karen for many years collaborations and also some discussion our methods, and also from some other from Serbo, from the Eagle, they give me many helpful discussion. And for here, in this talk, I mentioned so many works, and that I collaborate with many Chinese colleagues here. I thank all my colleagues. Okay, thanks a lot. Yeah. So
yeah, and we thank you, Changqing, for this wonderful talk with sort of a large number of really beautiful results, so that people could think a bit about questions. Maybe start. You you mentioned how to detect your effects, for example, for the vortex by looking at the pair production. You had also some experimental feasibility studies, I think, for the positrons, right? Maybe you can elaborate a bit more, especially on the vortex beams, how difficult it is to generate those beams. Do you see any major challenges to implement this? What would you be most concerned about to implement those ideas? It's easy to detect, them later by looking just at the pairs. But how do you do it? The parameters, I guess, are quite demanding, right? And
yes, actually, recently we already done some experiment, and we already found some very nice signatures. The main idea is, if the gamma photon it has a vortex, have the orbital angular momentum, we can think about if the gamma photon energy is lower, is lower than MeV, that's 100 keV, we can consider, the gamma photon interact with the Coulomb field of the atom. And also we can see the scattered electron distribution. From that we can distinguish the vortex. Or if you go to the high energy for MEV, we can use what gamma photon shooting on the target to see the Hitler effect. We also can see the difference. Actually, that's why we are preparing the work. And as I also mentioned, above 10 MeV, okay, you also can use the photonuclear reaction. We can detect that, okay. But in our recent experiments results, for that I collaborate with some other Chinese group. We already found some very interesting signature that is very
okay.
Yeah.
So it can be implemented. You have implemented it, but for lower energies yet, right? But if you go to the GeV regime, I guess it will be a challenge to do it, right?
If GeV, we should consider like the Beta-Wheeler effect with the strong laser. That is
It's difficult. Okay, but sounds good. Okay, so we don't want to spend too much time, so give someone else to ask another question. Let me see if there is anybody. If I don't see it, just speak up. Okay.
I'd like to ask a question, if that's okay.
Yes, please go ahead, Eva.
Thank you. So first of all, thank you for a really interesting talk. I wanted to ask about, your slide on laser solid target interactions, where you talk about like different contributions to your to your pair production signal. You have like the Bright-Wheeler contribution. Yeah, this is it. So maybe I missed it, but I would also expect there to be like a contribution from Bremsstrahlung, which would probably obscure like the signal that you're interested in, right? Because the positrons would have like a different like angular momentum. Have you looked at like the significance of that contribution?
Yes. Yes, it's true. Actually, for the Bremsstrahlung and also for the Hitler effects, for that we all already calculated, including in our effects already. Yeah. Also for yeah.
Okay, thank you.
May I ask one question?
Yeah.
Yes, please go ahead.
Yeah, I have very naive question. On the state of single gamma ray, I don't know if I learn from the Laguerre-Gaussian mode,
Yeah.
the individual field must have longitudinal mode, electric mode and magnetic electric field and magnetic field. So it should have longitudinal mode. And then if you convert into single gamma ray, is a gamma ray is longitudinal mode or I don't know.
This is very, important question. I mean, we also think about that. If we consider the laser is not the cyclopyrite, we consider it's a vortex. I mean, like you said, is the Laguerre-Gaussian or even other vortex say mode. Then the gamma photon itself has some okay. There can be different modes because they have a mixed state. Is a mix. To be honest, we haven't finished those calculations yet because in this quantum calculations, typically we should consider if we consider the laser is the Laguerre-Gaussian calculation is very very complicated, but we are calculating that. But honestly, recently we have some experiment. We use the electron interacting with Laguerre-Gaussian laser. We found something very interesting, but we haven't finished
it looks like a massive photon. That's my core question. Is that looks like massive photon? Because it may have a longitudinal mode.
For that, I cannot answer a question clearly so far because we haven't finished the calculation yet. Yeah.
All right. It sounds very.
But we are calculating that, so we want. We want to know the results. Yeah.
Because we must concern about the gauge invariance.
Yes, you are right.
It's really important and interesting.
Yes, you are right. Definitely. Yeah, but that's if we, because here we calculate for quantum method, this calculation is very difficult. But we are calculating that. We want. I hope in some time I can answer this question. Okay.
Okay. I'm looking forward to seeing that paper. Thank you.
Okay. Thank you. Yeah.
Okay. I think we should move on. That's okay. And let's thank Zhangjing again for this wonderful talk and these many results. And now we move on to vortex electrons from vortex gamma photons. So it's and we'll have another friend here, a new friend, I have to say, Lianglan Ji from Shanghai, from also a very famous institute. And please, you have 20 minutes. Please go ahead, Lianglan.
Hey.
I don't have no noise. Perfect.
Yeah.
Good to
can
see
you hear me?
Yeah, we hear you perfectly.
Yeah. Okay. Thanks. So I just first of all thank the organizers for the invitation, and I actually updated my title a little bit to QED scattering with quantum vortex states. I'm going to talk about not only linear processes but also nonlinear processes. So so first I'm going to introduce what kind of features these quantum vortex states will have, and what kind of features does it bring to the scattering process. And I'm going to show you a few examples for the scattering of vortex particles. Especially, I'm going to focus on the Bragg-Wheeler process. And then I'm going to show you an approach to generate these high-energy electrons with vortex wave functions in nonlinear scattering with circularly polarized laser pulse. Okay, sorry. So for this quantum vortex state, basically in these works, we use the Baser mode, which is constructed by coherently superposing plane wave modes with an helical phase here. And this state is an eigenstate of the TAM projection for not only the photon state, but also a lepton state. So it carries intrinsic orbital angular momentum, which is relevant to nuclear and particle physics. This is very different from this extrinsic orbital angular momentum like you have from a beam of point-like particles, and you do statistics, you get a macroscopic orbital angular momentum. So these are extrinsic OAM, which is not relevant to nuclear and particle physics, which we're not interested in this case. So another feature about this quantum vortex states constructed by plane waves, the Basel mode, is that all the plane wave modes, the momentum form a cone with an opening angle theta. So it has a longitudinal momentum bz, it has an amplitude for the transverse momentum, but the orientation is uncertain. So they only form an opening angle without a direct pointing orientation. And it has a hollow transverse probability density, as you show here. So there is a singularity in its wave function density. And of course, it has a loop azimuthal current flow. So there have been quite some studies on the scattering of these quantum vortex states. For example, with a single vortex state in A and B, with a double vortex state in C and D, and even with triple vortex states. Here I have a few things to say about these interactions. First of all, by describing the final particles in vortex states, you don't change the total cross sections. Okay, so the cross sections, these two approaches are consistent to each other. And in single vortex processes, they are basically incoherent average of all the scattering channels from the different plane wave modes. For two vortex processes, it leads to remarkable interference of different plane wave components. The third one, I think, is particularly interesting. So why there is that? Here is an example to show how this coherence happens. In molar scattering, you have two vortex electrons. From this amplitude of the scattering, we see that for a fixed final momentum of the particle, here is the capital K here. Basically, because you have a freedom to choose the transverse momentum, so there basically you can have multiple configurations to fulfill the resonance condition. For example, Ka1, K2A, and then K2B and K1B. Okay, so basically you have the resonance not only happens in plane wave scattering, the resonance only happens following this very strict four momentum conservation, but here the resonance happens in a range of in the momentum space of the incident particles, and these multiple channels from this interference can change the distribution of in the phase space of the final particles. Here you can also see here from the square of the S matrix, this interference term is more like a two-slit interference in the momentum space. So in this broadened resonance regime, you see that these fringe distributions are resulting from the quantum interference from these multiple channels that I show you in the previous slide. So why are we interested in this vortex state? Because spin is not enough. I have shown this example for several times. Here we consider the Bragg-Wheeler process with two gamma photons scattered with each other into an electron-positron pair. And if we only consider spin, initially we can have 2 h-bar of total angular momentum. We can have 1 h-bar in total for the electron-positron pair. So there is 1 h-bar missing in this equation, which we think intuitively that this goes to the orbital angular momentum of the electron and positron pair. So then we use this quantum vortex state to describe the electron and the positron to resolve this process. And from this, I will not go in detail of these calculations. So from this S matrix, we can see the 3 conservation laws here. This first delta function is the conservation of energy. The second one is the conservation of longitudinal momentum. In this case, the transverse momentum is not conserved because it's uncertain, right? And also in this matrix, you see these delta functions corresponding to the conservation law of total angular momentum. Basically, essentially the selection rules on the left is the spin of the incident photons. L1 is the OAM for electron, L2 for positron, and delta is determined by the spin states of the final particles. So here we apply this theory and we obtained these numerical results. The scattering probability as a function of the OAM number of the electron and positron. So when the spin of the incident photon cancels out, you see that the scattering probability is all symmetrical about OAM of 0. That means in this case, because the initial angular momentum is 0, the electron and positron, they don't gain any net OAM. But when the initial photon, their spin orientations are parallel to each other. So just like shown in this equation, you have 2 h bar of incident spin angular momentum. So the electron and positron, their scattering probability, their symmetrical axis is shifted towards by 1/2 for electron and by -1/2 for positron. So in total, they control 1 h bar. They contribute to 1 h bar of the angular momentum and conserve this equation beautifully. So I think what is interesting from our side is that it is very important to see that even the initial photons are not vortex, only plane wave modes. We can still create particles carrying vortex features in this case. Okay. And then we move to describing. We move to the case where the incident photons are also vortex, describing by the Basel modes. And then again, we see the TAM conservation law, and we reproduce the resonance, broadening of the resonance condition here. So for example, for plane wave scattering, you see the resonance happens only in a very thin line following strictly the full momentum conservation. But here, because the transverse momentum is not conserved, you see the broadening of this resonance condition here, and the interference from multiple channels are also shown from the fringe distributions from this vortex Brad-Wheeler process. Okay, and this vortex effect actually exists in various scatterings. Here we show another example. In Bremsstrahlung, we can see that for a plane wave electron, which is spin polarized, it can transfer its spin angular momentum to the orbital angular momentum for the electron and for the gamma photons. And when the incident electron is also vortex, then in the parameter regimes we consider here, most of the orbital angular momentum actually goes to gamma photons. So here shows that the gamma photon takes almost all of the orbital angular momentum from the electron. And also this is also the case. This theory is also applied in another process called Bethe-Hadler process, with the photon decaying into a pair of electron and positron, and they show the transfer of orbital spin angular momentum to orbital angular momentum, and from orbital angular momentum to orbital angular momentum. Okay. So the next question is how can we produce this kind of vortex particles? And Jianxin in his presentation also mentioned this. So for low energy photons or electrons, there are a number of quite effective approaches. Spiral phase plates for hologram or magnetic monopoles. Now, for example, 300 keV and 100 h bar vortex electrons can already be generated. But as I said, we are more interested in high energy ones. This is quite challenging because their wavelengths are extremely small. So the previous approaches are actually invalid. They cannot be used to manipulate the wave functions of these high energy ones. So for photons in the X-ray regime, you can produce that from a helical undulator. And for gamma photons, there is a proposal from inverse Compton scattering by sending high energy electrons colliding with vortex laser, for example, in a Lagrange-Gaussian mode. And then the scattered gamma photon can take almost all the OM from the incident vortex laser pulse. So it seems that this case, together with the previous studies I showed to you before, indicates that QED scattering is a very efficient approach to transfer angular momentum. But there have been no approaches showing that high energy electrons can be also twisted. So this is the main topic of the third part of my presentation. We propose to generate high energy vortex electrons in collision of high energy electrons with a relativistic circularly polarized laser pulse. So the basic idea is that when the electron absorbs up to millions of laser photons and radiate an high energy gamma photon, there's not only transfer of energy here or momentum here, but also angular momentum, and the huge total angular momentum from the N laser photons will necessarily transfer to the orbital angular momentum for the gamma photon and electron. The question is how to resolve this process to see how this happens. So we developed this nonlinear vortex compton scattering theory to find it out by describing the incident electron in the Volkov state here. This is already very well known, and the emitted photon in the Basel mode, in the Basel state. A very challenging part is the electron, which is not only dressed in the laser field, but also carrying orbital angular momentum. So we describe it using the Volkov Basel state here. And there is something quite interesting about this Volkov Basel state. We plotted the transverse density of this wave function at different phase from 0 to 2 pi, basically in one laser circle. So we see that this very localized distribution, the symmetric axis, the symmetrical center actually circulate around the red circle here, around an axis. So this is exactly the typical trajectory of a classical point-like electron in a circularly polarized laser. So this corresponds to the extrinsic orbital angular momentum, which will vanish when it passes through the laser pulse. So this is not something we want. We're more interested in this each compact waveform here. It has a transverse flow following the blue arrow, the blue circle here. This corresponds to the intrinsic orbital angular momentum of this Volkov Basel state, and it can be described exactly with the quantum number L in this wave function. So that's what we want to find out. That's what we're interested in. Okay, so these are the main results. Here we show the scattering probability as a function of the laser photons absorbed by the electron. And as you can see here, as the photon number increases, the central energy of the emitted photon actually deviates from the dashed line. This line is obtained by neglecting the radiation reaction effect. So it means that the radiation reaction leads to this energy downshift of the emitted gamma photon, which is already well known. Something new is shown in figure B here. Here we show the distribution as a function of the angular momentum number for the electron, the blue ones, and for the gamma photon, the red ones here. Now we see that when the laser absorbs moderate number of laser photons, for example, 100 and 1000, or 1000, we see that the gamma photon actually obtains almost 100% of the angular momentum from the laser field, from the laser photons. But when the absorbed photon number goes beyond 10,000, the electrons are gaining more and more angular momentum, and the gamma photons are getting less and less. Here this angular momentum number is normalized by the photon number to see exactly what partition goes to electron and what partition goes to the gamma photon. Here you can also see that the distribution shows a symmetrical axis here, and it has also a spread that is almost linear to the absorbed photon number. So it looks like this radiation reaction can introduce a vortex effect, or can twist the wave function of the high energy electrons in this case. And this can also be seen from the wave functions for the electron. For n of 100 and 10,000, there is no singularity in this wave function, but when it goes to 10,000, the singularity appears, which is a typical sign of the vortex structure. And next, we want to quantify how radiation reaction determines the electron OAM. Here we, for the dots are from the numerical results from the cross sections, and the lines are from our theoretical model. So we define a quantum number chi here, which is the photon number divided by the electron, the photon energy divided by the electron energy. And surprisingly, we see that the electron central orbital angular momentum is just proportional to this number. And you can see here, this equation describes the partition of the orbital angular momentum to electron, the solid ones, and to gamma photon, the dashed lines, very well. And it also shows that this radiation reaction, or this high energy electron, can be twisted even for a naught of 1 And of course, for A naught of 100 is more efficient, but it already is significant for A naught of 1 and A naught of 10, which this kind of laser pulses are already accessible in many laboratories. Right. So next question is, when we have these vortex electrons, how do we know they are twisted? So we did another calculation to collide these electrons to another laser, which does not have to be quite intense. We actually use A naught of only 1 here. We see that for vortex electrons, it shows a double-peaked gamma photon spectrum, and this results from the 2-angle configurations, as I just showed you in previous slides, from these opening angles that formed by plane wave modes. This is not going to happen for non-vortex electron. It has only 1 single peaked spectrum. So this is I think is a quite clear evidence to identify these relativistic vortex electrons carrying intrinsic orbital angular momentum. Finally, these kind of particles we think are quite interesting for nuclear physics and particle physics. For example, there is one work showing that these vortex electrons can be used to enhance the Nick process, which requires high total angular momentum transfer from initial particles. And also very recent ones showing that unpolarized twisted electron positron annihilation can produce polarized mesons, which can provide a probe of spin and parity sensitive observables. Okay, so I conclude my presentation here. I think I show you the scattering of quantum vortex states in the linear and the nonlinear regime. In the nonlinear regime, I show that using circularly polarized lasers that are accessible in most laboratories, we can produce these high energy electrons with twisted waveforms. And I thank my group members from our institute and my collaborators. And thank you for your attention.
Yeah, we thank you, Liang, for a wonderful talk, which is now open for questions, please. Oh, yeah. So Jianxing is already the first one, please.
When I talk, Liang, and I'm wondering, do you have some experimental plan to generate like the high energy vortex electron?
Yeah, thank you. Yeah, thank you for the question. Yes, of course, as I just showed in this last part of the presentation, it doesn't require laser intensity of extremely high. You reach the A naught of 1, which should be enough to generate these kind of electrons. And also, if we want to measure them, we can do another scattering with a moderate relativistic laser pulse, and that should be enough.
Here, actually, I'm thinking about to first generate, use the traditional method, the vortex electron, then use maybe small, accelerator to accelerate the vortex electron to high energy.
Yes, that's also a very interesting approach. Yes.
Yeah, then because I'm thinking about if we just inject those vortex high energy, so the 100 MeV, the vortex electron to the free electron laser facility, maybe if the electron have maybe the very high the OM, what will happen if we in the X-ray laser? Would maybe the OM can be very high? Could be.
Yes.
Yeah.
Yes. Yeah. Very interesting topic.
I think if we maybe sometime we can face to discuss the details, because we are also thinking about how to generate the use FEL facility to generate the high the OM the X-ray. Then we think about use the vortex electron, but first we should experimentally generate those high energy vortex electron. So I think you have those facilities. Maybe we can think about for the experiments, yeah?
Yes.
Okay.
Yes,
okay.
Definitely.
Cool.
Yeah.
Okay.
Okay.
Thank you.
Cheng, you're next.
Thanks for a very nice talk. I have one question regarding how to identify intrinsic electron OEM in experiments. So for the extrinsic OEM, we know that if we observe an electron kind of a circular distribution in its number, so it could be understood as extrinsic. But for intrinsic, do you have some direct measurement method to identify this intrinsic electron? Yeah, OAM.
Yes, so very good question. At the moment, I think a possible approach is just as I presented in this slide. So basically, when you have these electrons with a quantum vortex feature, the scattering, so the emitted gamma photons, if you look at the spectrum, it has a double peak, right?
Yeah.
It has two peaks. And these two peaks do not exist for non-vortex electrons. Basically, all you do is to resolve the spectrum of the generated gamma photons. You put a detector there, and you measure the spectrum of the gamma photons along some direction. And then if the spectrum is good enough, you can resolve these two peaks, and then you can see these are from the vortex electrons with intrinsic orbital angular momentum.
Yeah. Okay, so. But by the way, is there any other? So here is kind of observe the photo emission from the electron. So is this the only way to identify this intrinsic OAM as far as you know?
Yes. So I think one possible way. This is just an idea popped out from my head. Yeah. Maybe we can send these electrons to collide with nucleus, and if we can see from the diffraction pattern. Because there's also a diffraction from this vortex, wave functions by the Coulomb field. And if we can find this diffraction pattern from the vortex state, maybe there will be some clue to detect that.
Okay, thank you very much. Very impressive. Thank you.
Maybe one could look also like Jiangjing at pair production, right? If you look at higher intensities or so, right? I mean, Jiangjing had with his gamma photon, his vertex photons, he looked at the pair production, right? And he looked at which was the moment was different, right? But here, of course, maybe the threshold is too low for getting pair production, I guess. But I thought it was also an interesting way of seeing signatures of vortex particles, because that was, of course, the generated pairs were, of course, quite different. But I guess you need to go beyond the threshold, of course, to get there. But anyway, very interesting. I think we should move on. I'm sorry, we're a bit running already a bit late.
Yeah, thank you.
But I'd like to thank you for this wonderful talk. Beautiful results, and of course, like Jiangjing, maybe hope they will be implemented experimentally at your nice facility. So that would be really fantastic. So I think we have now the next speaker. Professor Yu Shen. Another friend, so it's a good day for me today. So she's a professor in China, and she will talk about, let me just get this to lepton polarization in the reflection regime. Please, the stage is yours, Yu.
Okay. I have some problem to share.
Don't worry. If there's a problem, we can swap you with Yanfei, but just try a moment. We're not so bad in time. Just try it, and then if it doesn't work, we do the other one first, and then do you afterwards.
So maybe Yanfei can start first. I will.
Yeah. So it's no problem. Yanfei, are you around?
Okay, I get first.
So okay, we just swap the order. I think that's not a problem.
Take your time. Yeah. Can I share the screen?
Yeah, okay. I remember this room from your last talk, this background. So that's good to see you also, the last friend also. Yanfei has been spending a while with us, and also a wonderful scientist, and all four. It's a great day. So, and you will talk about strong signatures of one loop self-energy in the polarization resolved nonlinear quantum scattering. Please go ahead. And the sharing works in your case. Wonderful.
Okay,
please.
That's critical. Yeah, here. Hello, everyone. I'm Yanfei Li from Jiaotong University of China, and I'm very honored to have this chance to introduce one of our new works, Strong Signature of One Loop Self-Energy in Polarization Resolved Nonlinear Quantum Scattering. And the works include me, Yue Chen, Karen, Antonino, Matteo, and Crystal Kettle. They four of them come from Max Planck Institute for Nuclear Physics. And here, I will divide the contents into these 4 parts. Let's begin with the introduction. And the fast development of ultra-intense laser technology brings about new possibilities for the strong field QED in studies, especially in experiments. Okay. And based on the head-on clearance geometry. The head-on clearance geometry, since in the electron right frame, the electron will sense a field strength gamma times larger. Then it enables us to study QED effect in experiments with pet-watt laser facilities at present and with the next generation pet-watt laser facilities. Here, we focus on the QED process. We focus on the QED polarization effect during this process. The nonlinear complex scattering and the nonlinear Bethe-Wheeler process. And here there is one important issue, is that the polarization dynamic of the particles during this interaction process. To finish the problem, to describe the polarization dynamics, we developed a new theoretical method for the calculation by 3 steps. First, we study the seed electron spin polarization. In the second step, we study the photon polarization, the emitted photon polarization. In the third step, we finish the problem about the new created pairs spin polarization. And during this time, we put forward new schemes on polarized electron source, polarized gamma ray source, polarized Poisson source. And we also put forward new scheme for electron polarimetry and for the investigation on helicity transfer effect during complex scattering. And recently, we studied the signature of one-loop self-energy in polarization resolved nonlinear complex scattering. In this work, we aim at single out the signature of OLSE during the interaction. But how can we do this? Then we need to design the scheme for our purpose, to single out the OLSE signature. Well, in strong background fields, the electron polarization dynamics has been described by Baya using operator approach of strong field QED. And the polarization picture given by Baya can be illustrated, and shown by this figure, can be illustrated using QED technique of Feynman diagrams in Fourier representation. And let's see these 3 diagrams. The first diagram is related to spin precession. It can be described by the famous BMT equation. And the second one is related to radiative polarization at 1 photon emission. And the third diagram is the interference diagram of OLSE with the forward scattered one. And here I will list them here. And the second diagram, the radiative polarization effect, actually it includes 2 contributions. One is due to spin Philippe. We have known it a lot. And the other one is the spin span is due to spin dependence of photon emission probability. I will explain it later. And the third diagram corresponds to the OLSE contribution. It also includes 2 contributions. One is due to non-radiative polarization effect. I also will explain later. And another one is the modification of spin precession due to the electron anomalous magnetic moment. And these three parts are well known. And here I want to explain these two effects I shown by this figure. Actually, these two effects appear together and with the same strength. And these two effects result from the radiation probability. The radiation probability tells us that if, electrons with during the interaction, the electrons with spin anti-parallel to the B field in the electron rest frame. And these electrons are more likely to emit photons than the electrons with spin and parallel to the B field. So here, if we have an unpolarized electron beam interacting with a B field, for sure, here we ignore the spin flip effect. We just focus on these two effects. Okay, after the interaction, this electron beam can be divided into two parts. One is radiating part, the other one is non-radiating part. And the radiating part, the electrons in the radiating part have emitted photons. Well, this electron in this part haven't emitted photons. And apparently, there are more spin-up electrons in this part. And in contrast, there are more non-radiating there are more spin-down electrons in the non-radiating part. So we can say both of these two parts are polarized due to the spin dependence of the photon emission probability. And we can say the polarization of this part corresponds to this effect. The polarization of this part corresponds to the non-radiative polarization effect. We call it NRP for short. And here we aim at identify the OLSE signature. And since a lot of works have investigated this electron anomalous magnetic moment, here we mainly focus on this effect, the NRP effect. So we will single out the NRP signature and provide a method to detect it. Here we can know that it is for our purpose. It is necessary to separate the non-radiating part from the radiating part for our purpose. And since this part, electrons in this part are nominated by NRP effect. And it is obvious that the signature should be an opposite polarization direction of these electrons compared with the other electrons. So if we can create a scheme where we can single out electrons dominated by NRP effect, and we found that the polarization of this effect, these electrons, so opposite polarization directing with the others, then we succeed. And now we have a simple design scheme. And do we succeed? It's not easy. Why? Since we can see that by this figure, the panel A, the RP effect is more powerful than NRP effect for electrons, since the RP effect also includes the spin flip. So if every time the NRP effect will be covered by the RP effect, as shown by this figure, since it indicates the spin variations induced by RP effect and NRP effect. And it seems that we need to, if we want to do this thing, we want to single out the NRP signature, we should select small chi. K is the quantum strong field parameter. But some previous papers tell us no, we can't get an obvious signature. And here in this work, we demonstrated that a large chi will provide a new way for our purpose. We should take advantage of the stochastic effect of photon emission for large chi. Let's see this figure panel B. It indicates the spin variation via RP effect, radiative polarization effect. And we can see that for an electron, when the spin variation is close connected to the emitted photon energy. Then when the electron to emitted photon with lower energy, the spin variation will be small. So if we can find a part of electrons, and these electrons emit photons, but with lower energies, and then the RP effect on them will be reduced, will be suppressed, will be weakened, and then, but at the same time, the NRP effect keeps stable. So this part of electrons will be dominated by NRP effect. We need to single them out for our detection. So here we design reflection region to single out these electrons experiencing weak radiation coils. And so by this figure, we use a circularly polarized laser pulse to interact with an ultra-relativistic electron bunch. After the interaction, electrons radiate a lot, will be reflected by the laser pulse, while the electrons experiencing weak radiation recoils will penetrate through the laser pulse, and finally keep moving forward. And so by these blue circles, so if we need to single them out for our detection, and this is our scheme. So now we have finished designing the scheme, and then let's see the result. Do we succeed in identifying the NRP signature? Here are the results, and we use the laser pulse and electron beam parameters at least on the left side, and we get the simulation result on the right side. Here panel A is the electron number density distribution versus the final electron energy and the scattering angle, and theta is also the polar angle. And we can see that when theta is smaller than 90 degrees, the electrons keep moving forward, and electrons with the theta larger than 90 degrees are reflected by the laser pulse here. And panel B is the electron polarization distribution, and we can see that electrons keep moving forward. So a minus here the color bar is the polarization. And we can see this part of electrons, so minus polarization, while the electron reflected, so positive polarization. And then we can see the electrons with electron here, well, dominated by an RP effect, and so an opposite polarization direction. And for the convenience of experiment, we introduce a experimental measurable parameter A. A is the symmetry parameter of molar polarimetry, and this parameter can be detectable in experiment. And we can see that electrons with small state, and so minus signal while the electrons reflected, so the positive signal, and the signal strength is far larger than the current experiment capacity by others. So here we have got an obvious NRP signature, and in experiment, if we want to enhance the detection efficiency, we can collect the electrons within an angle range. We can like shown by this line. If we can collect electrons within within 60 degree, then we can still get a substantial signal strength. And so here we succeed in identifying the NRP signature, and the signature strength is large enough for the experimental operation. But I wonder, I think some people may ask, since you need here, you choose angle selecting technique for the signature detection. Why don't you use the energy selecting technique? Actually, we have also studied possibilities for NRP detection with energy selecting technique, and we get the signal as shown by this red line, and compare with this line, we can see that we can still can find the opposite polarization direction. We can still get the signature signal, but the signature signal strength is cut by half. Why as energy selecting technique is worse? And here I will explain. And you can see that this figure and the vertex axis are the average radiation energy loss. This is for each electron. This is for each emitted photon. And from these two lines, we can see that the radiation loss the radiation loss of the electron is closely connected with the theta, with the scattering angle, and their relationship is linear. Like yes, they show a linear relationship. So we can use the angle selection technique for our purpose. But the relation between the final, as shown by this figure, the final electron and energy with the radiation loss is complex. So electron here, this part electron will emit more, but the final energy is higher than this part. That's because the laser pulse will accelerate the electron at the same time. So their connection is complex. So we can conclude that the angle selecting technique is more sensitive compared with energy selecting technique in our scheme. But we can use we can combine post angle selection and post energy selection method together for a higher signal strength, as shown by this figure. Here we also study the signature with the changing of the electron beam and the laser pulse parameter, and we have also studied the influence of fluctuations of the laser pulse parameter. This figure is the influence of fluctuations of electron beam parameter. We can see that even this parameter change, the signature is robust. And so we finish our work. In conclusion, we have put forward a scheme to identify the distinct signature of the electron NRP, described by the contribution of the QED by loop self-energy correction in electron and laser beam collision, employed in the radiation-dominated reflection regime, an experimentally accessible signal of election polarization higher than 10% positive to the driven laser helicity for electrons collected within a specific small scattering angle will indicate the signature effect. And the signature is robust with respect to the laser and electron beam parameters and measurable with current available experimental technology, providing a way for an experimental detection of the QED prediction on self-energy corrections via intense laser-driven spin dynamics. And that's all. Thank you for your attention.
Yeah, thank you for this beautiful talk, Yan-Fei. We're a bit actually quite late, so maybe we can not have a short question or two. If there is anything, please. Any questions? Maybe one. I don't see any. If I don't see it, maybe just speak up.
Okay,
yes.
Probably, may I ask one question?
Yes, please.
Okay.
Thank you so much for this interesting talk. Could you please show once more time what are typical chi values of your setup when you collide electrons with your laser field?
Okay, this is the parameter.
Yes.
Yes.
So
chi is about 1.
So it's about 1. I'm wondering that typically, like if you don't consider loop radiative correction, you would see that most of the electrons probably are deflected by the laser pulse. Maybe I just missed it in your talk. What would be the percentage of electrons that go through the laser pulse and have a chance to have a spin flip because of loop correction?
Okay, let's see here. So, you mean how can we get this part of electrons penetrate?
Just how many electrons penetrate the laser? Yeah, that's just my simple question.
Okay, let's see here. You can see this. You can see by here this line. This is the election number density profile. And so we can see here, this is the ratio and proportion. And penetrate over, okay, let me think here. Okay, this is -1, and maybe less than half of the electrons will penetrate through the laser pulse, but the electron with small scattering angles we need for detection will be maybe 0.1%.
Okay, I see. Do I understand correctly that you can tell for sure that spin flipped occurred because of loop correction only for those electrons that are almost not deflected? Is it correct?
I'm sorry, I didn't get your question.
Okay, let me write the question in the chat so that it's clear. So,
okay.
So thank you a lot. Thanks a lot.
Maybe you can do the chat and answer in the chat that we can move on.
Yes.
We're a bit late already. That would be the best way. Thank you very much. And then we could try already with you if she can share her screen maybe. So Yan-Fei, maybe you can share already that we can see if it works now for you. But let us thank Yan-Fei for this wonderful talk. So excellent. And Thank you very much. And I'm really relieved and pleased that even though, of course, it was nice to see you before, but now we see her.
Can you see the screen? Can you see the slide?
The screen. Yeah, perfect, beautiful.
Sorry for the mess.
No, don't worry. It's. I mean, these things are not a problem. And so you have 50 minutes. So please go ahead. And we have again another talk on in the reflection regime, and now on laser-driven lepton polarization. And please, you go ahead.
Okay, thank you. And today I will introduce a new way to produce polarized electrons and positrons using reflection. And our motivation is polarized electrons and positrons are very valuable tools to study nuclear physics and high energy physics. And recently, the rapid development of laser technologies, now today's laser can already deliver a laser intensity of 10^22 watt/centimeter², and this value will increase to 10^23 to 10^24 in the next generation laser facilities. So some of them here. And recently, there are many schemes to use strong lasers to produce polarized electrons and positrons. However, the lasers are usually very symmetric, you see. So the electrons, for example, the electrons go inside of the laser. The spin down electrons are actually pointed to the negative Y, because of the radiative polarization. And however, in the next half cycle of the laser, the electrons are polarized along the positive Y. So because the laser is symmetric, after the interaction, the electrons and the positrons actually have almost zero net polarization. And so it's straightforward to think maybe we could use a symmetric laser to produce polarized electrons and positrons. One possible way is to use the two-color laser pulse, and we have tried this method. Finally, obtains polarized positrons with polarization goes up to 6% polarization. It's also possible to use initially polarized electrons, and because of the helicity transfer during this process, we finally get longitudinally polarized positrons with polarization could reach to 100% polarization. Another way is use elliptically polarized laser. Electrons Compton scattering with such kind of a laser will split along the propagation direction, and different spins will go to different angle regime. And with this method, they could obtain polarized positrons with polarization degrees goes up to 90%. And recently, there are schemes to use laser solid interactions to produce polarized positrons, and they also can have some transversely polarized positrons. Now, the question is it possible to obtain polarized electrons and positrons with symmetric lasers, very simple lasers like linear polarized laser, because it may be very difficult to construct asymmetric lasers with very high intensity or prepare initially polarized electrons. Our solution is use the reflection. So if we use reflection, even though the laser is symmetric, but the interaction could be asymmetric because the reflection. See the parameter we use, that is the laser, we use the next generation laser, and we use GeV electrons. The parameter we used is in a quantum radiation dominated regime. In this regime, the electrons could lose most of its energy and being reflected. And hopefully we could get some polarizations because of these asymmetric interactions result from reflection. And before showing our result, I would like to have a few words about our Foley spin and polarization resolved Monte Carlo simulation. So first of all, we should go back to 2019, and they have developed a code for nonlinear Compton scattering. However, in this code, all initial and final spin of the electrons are resolved. The photon polarization is unresolved. With this code, they could produce polarized electrons with elliptically polarized laser. In the same year, we use a similar code to study the Brita-Wheeler process. And we use two-color laser pulse produce the polarized positrons. But unfortunately, the photopolarization is still unresolved. And 1 year later, we finally have the code, fully polarization resolved the code for nonlinear Compton scattering. Both the electron spin and the photon polarization are resolved. With this code, one could have polarized gamma rays. And we also have the fully polarization resolved code for Brita-Wheeler process. At this point, we have a fully polarization resolved code. And with this code, we started the helicity transfer and get longitudinally polarized positrons. Recent years, we are more interested in studies the radiative corrections in nonlinear Compton scattering. We found distinct signatures of radiative correction, which Professor Yanfei Li already introduced in the previous talk. Okay, with this fully polarization resolved Monte Carlo simulation, we finally got our result. Let's first look at the seed electrons. And the electrons are polarized transversely. The highest polarization degrees could reach to 20%, and the electrons are polarized along laser polarization direction, which is defined as the X direction. It's also polarized along Y direction, which is the magnetic field direction. One can see that the polarization is very angular dependent polarization is very symmetric here. And also the small angle polarization is opposite with the large angle polarization. So the polarization feature is kind of very rich here. And we investigate firstly, we investigate why the electrons are polarized along magnetic field direction in the large angle region. To study that, we have collected electrons goes to this large angle, and we trace their trajectory. We find that the electrons that are initially with very large X are positive will finally get out of the laser with zeta Y positive and px positive. Well, the electrons that goes here that are initially have position X negative, they will finally have px negative and the polarization zeta Y negative. Which means the final momentum px and the initial position x is correlated. And this is the simulation result, which just shows these physical pictures here. And next question is why this initial coordinate is related to the momentum, final momentum, and the polarization. It's because when these electrons with X positive go inside of the laser, it may collide with the laser, reflected and accelerated to the relativistic velocity. Such kind of electrons will move with the lasers, and it stays in this acceleration phase for a really long time. And if this, because when it stays here, the px is positive. If the electrons is distributed with a very large positive x, then it may have a good chance to pass out of the laser at this phase. So our simulation shows that some electrons pass out of the laser in this phase. If it because it still has the simulation, some electrons goes per a little back by the next half cycle, but finally they will outside of the laser in this acceleration cycle. So, why the momentum and the polarization is correlated? That is because the polarization is a result from the radiative polarization of the electrons. So, the radiative polarization is in phase with the time evolution of px. If the interaction stopped here, I mean, if they reflected out of the laser at this phase, then one could say that it will have final momentum ps positive and zeta y positive. This simulation figure also shows that if these electrons finally have zeta y positive, they will finally have px also positive. Okay, So why the electrons are polarized along electric field direction? This is purely because the spin precision governed by BMT equation. We can see that we collect the electrons goes here, and if this electrons before it meets the laser peak, it have very small Vy. In this phase. In this range, the zeta x is almost zero. They only have radiative polarization result zeta y. But after it meets with the peak, the strong Ponder motive force pushes the electrons towards y positive. It gains a Vy, so the spin vectors rotated from zeta y to zeta x. After that, the zeta x is emerged, but the zeta y is decreased. If one artificially turns off the spin precision, and one will find that they only have zeta y, they don't have any zeta x. The last question is why the small angle region's polarization is opposite with the large angle region polarization. We collect these electrons, we trace their trajectory, and we found that those electrons are mostly comes from the beam center. Initially, they are in the beam center, so after reflection, they're still caught by the laser. They're still moving with the laser, so the momentum is still oscillate with the laser field. However, the spin, the radiative polarization is strongly suppressed after reflection because K is very small when the electrons, the laser are in the same direction. It would be like this: the electrons goes into the laser reflected, and when it because the radiative polarization, it has px positive and zeta y positive. If it is a large angle electrons outside of the laser here, then it will have a correlated momentum and polarization. However, if it's on-axis electrons, it will keep moving the laser, so but the polarization is unchanged. The px changes the direction. That's why the small angle polarization is just opposite with the large angle. It's because the polarization comes from radiative polarization of the half cycle before. Okay, the pairs, this is a simulation of the pairs. Because we are working in the regime with very large A0, so here this quantum parameter chi, it could reach to 2, around 2. So in this case, we could have one initial electrons, we could have finally one pairs, which is the yield of the pairs is 1 order larger, it's 2 orders larger than the 2-color laser case. The angle-dependent polarization are very similar to the electrons. And with their trajectory, we found that similar to the electrons, the positrons at the px positive will find out of the laser with px positive and zeta y positive. So I will just skip this part because of time. Our conclusion is, even though the reflection scheme, in the reflection scheme, the polarization is not very high. It's only can get to 20% polarization, but the polarization effect in this process are very rich. We have studied the large angle polarization along magnetic field direction. We studied the large angle polarization along electric field direction, and also we explained why the small angle polarization is opposite with the large angle polarization. The most interesting things about this scheme is we may provide a very relatively simple way of produce dense polarized lepton beams because we just use linear polarized lasers. We don't need to construct very complicated asymmetric lasers. And okay, so this is my talk. Thank you.
Thank you also, Yu, for this beautiful talk and staying in time. So Sheng was first to raise his hands. Please go ahead.
Thanks for a very beautiful presentation. I have 2 questions. The first question is about, is this your reflection polarization scheme sensitive to the laser spot size?
Laser what? Laser size? Beam size?
Laser focal spot size.
Okay, I have a figure here. If the beam size is getting larger, the polarization zeta y will decrease. But if the beam size is too small, some electrons may just go forward instead of reflection, so this polarization will decrease.
Okay, so what is the meaning of the R? The reflection ratio?
Rate. Yes, ratio.
Okay.
How many electrons reflected?
Okay, thanks. My second question is for your positron polarization. Is this positron polarization come from the positron that is polarized before at the generation or after the generation?
I think both effect. Yeah, it's also produced with zeta y, but if it's produced with polarization positive and also it have X positive, then it possibly will unstable laser with P final momentum positive. Then both I think this is very similar with the electron. Even though it don't have initial polarization, it still will be polarized.
Okay, thank you. Thank you very much.
Any further questions, please? So we have a session. So if I do not see, I mean, if I've overseen it, please speak up. But I don't see any. So let me thank again you for this beautiful talk, but all four speakers for a great session. And we have, in 20 minutes, the next session, which will be also very exciting. So please join us and see you then. And till then, thank you.
Thank you.
Yeah.